This problem seems like it's pretty simple and straightforward, and it pretty quickly starts to get complex. So let's start off here. The scenario is a train engine pulls a train with 3 cars. Each car has the mass shown, and if you can't read it in there, it's 3,000 kilograms, 2,000 kilograms, and 1,000 kilograms. Suppose the cars are connected by metal bars with tensions indicated in the diagram. So here are the tensions, F3, so we can imagine there's a force right there, we'll call F3. Here is F2 in between the tanker and the lumber right here. So we can imagine there's a force right there. And here's F1 between the engine and the lumber car. So we can imagine that there's a force right there. So 3 separate forces. This is really important right here. It says the engine accelerates at a rate of 2 meters per second squared. The engine's pulling all of these, so that means all of these are in this system of the train. They're all going to accelerate at 2 meters per second squared. Assume the cars travel on bearings with negligible friction, so we won't add friction to any of our free body diagrams. So we want to sort of keep this in mind. I've kept it right here in this picture as well as we start to build our free body diagrams. And now on here, we want to start to add them. Let's start with the forces on the 3,000 kilogram car right there. So we know that there's going to be gravity acting on that one. And I made each square worth 3,000 newtons. Sort of, I have some foresight. I worked all the way through the problem. Otherwise, you might start working through it and have to redraw them there. So we can actually use right now, I don't know if you remember us using this equation to find the weight, which is the force of gravity. And it is simply the mass times gravity. So if we have a 3,000 kilogram car, plug that in there for the mass, multiply by g, round that to 10. So a 3,000 kilogram car should have a weight of 30,000 newtons. And if I make each square 3,000 newtons, then I got to make the weight here 10 squares long. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to label it all the way down there, and I'm going to call this FG3, the force of gravity on the 3,000 kilogram car, the third car, whatever you want to call it. And then likewise, I know, I'll just draw it all the way to the top here, that there's got to be a counteracting normal force on it. It's not accelerating up or down, so it must be balanced vertically. So I'll call this N3 for the normal force on 3 there. And then we've got to have a force that's actually accelerating it forward. It's F3 right here. F3 pulls it forward. And I'm actually going to, even though they ask it for it right here, do a little math here. Let's write this down before we draw the third force. They say they want F equals ma written here. Well, the only force that's going to be left over horizontally is force 3. And that is going to be mass. Now that mass in F equals ma is just a generic mass. So in this case, we're talking about the mass of object 3 times the acceleration. And we could actually figure out right now what this F3 has to be. So in order to have, we have here a mass of 3,000 kilograms, and we're going to accelerate that, they told us, at 2 meters per second squared. We can see 3,000 times 2 is 6,000 newtons. So the total force must be 6,000 newtons. So that actually means making each one 3,000 newtons there. That's only 2 little squares long there. So I'm going to call this one F3. So now let's come over here to the second train, the 2,000 kilogram car. So we know that we have got a normal force on it and gravity. Since I can do the weight again for the 2,000 kilogram car, multiply that by G10 and you'll get 20,000. So about 6.6 squares, 1, 2, 3, 4, 5, 6, close enough. And so we'll call this FG2 downwards. There's got to be a normal force balancing that out. 1, 2, 3, 4, 5, 6. I'll call that normal 2. Now, if right here we have the boxcar being pulled forward with F3, then we know that that boxcar's got to pull back with the same F3 on this one. So 1, 2, and I will label this F3 as well. I could call this one F, the force of 2 on 3, and this one the force of 3 on 2, but I'm actually just going to label them each F3 because it's one interaction pulling them together like that. And then we've got one more force, which is right here, F2. And so I'm actually, before I draw its length, I'm going to solve for it up here. So what are the total forces in the x direction on this one? Well, we got F2 pulling it forward, and we got F3 backwards over here. And then the mass here that's being accelerated is actually, we'll say, m2 times the acceleration. So what's this force 2? We're looking for that. We just solved for the force 3 over here. We said it was 6,000 newtons. And over here we have the mass, which is 2,000 for the middle car, and the acceleration is 2. So you can work out the math here. 2,000 times 2 will be 4,000, and then add this over to the other side there, and you will get, in that case, 12,000 newtons. I'm sorry, 10,000 newtons. So 4,000 plus 6,000 is 10,000 newtons. So that would be about 1, 2, 3, right there. So this one's just 2 long, and this one is basically 3 1/3. So we'll call this one F2. And then finally, this third one over here, we've got the force on the 1,000 kilogram car, the lumber one. It only weighs 1,000 kilograms. Multiply that by 10, and we get 10,000 newtons. So 1, 2, 3, roughly long. We'll call that FG3. We'll have the same normal force up, about 3 1/3 up. We'll call that the normal force on 3. If F2 is being pulled forward here on these 2 cars, then we know it's got to be pulling back the other way as well. And so 1, 2, 3 1/3 back. I will call that one F2 as well. And then finally, pulling on the lumber car here is F1. And so F1 here, we can actually solve for it again. Let's write it in here. We know we have F1 pulling forward, we have F2 pulling backwards, and that's going to be the mass of this one times its acceleration. So we can plug this in. We're looking for F1. We know now that F2, we solve for it over here, is 10,000. The mass of this car is 1,000, and the acceleration is 2. So if we solve for F1, we get 2,000 here, add the 10,000 over that side, and we get 12,000. So 1, 2, 3, 4. And we'll call this one F1. And so there are all the forces for the first diagram. I'll add the second diagrams on a second video.